Let's talk about representation of a group. So, given a group G, such that it has an element small g that belongs to the group G, the idea is to associate each element G with a D cross D matrix. That is, the matrix is given by D of G, such that my D of G1 composition D of G2 is equal to D of G1 composition G2. Alright, so the matrix D of G is then said to represent the element G and the set of matrices D of G for all element G that belong to my group. So in this case, my D of G is then said to provide a representation of my group G, and the size of the matrices, that is D, is then the dimension of my representation. So D tells me the dimension of my representation. So for example, I have a representation of a 3 cross 3 matrix, then it will be a 3-dimensional representation. Alright, let's look at an example. The example we're going to look at is the permutation group of 4 objects. So that is the S4 group. And suppose now that there are 4 objects which are my vectors, 4 vectors. So V1 is equal to, let's define it as 1 0 0 0. V2 is equal to 0 1 0 0. V3 is equal to 0 0 1. I'm sorry, 0 0 1 and 0. And finally V4 is then 0 0 0 1. So as you can see that my V1, so for this one I have non-zero entry at my first row. For this 2 in V2 I have my non-zero entry at my second row, and likewise for V3 and V4. Alright, then let's also take an element from my S4 group, that is, for example, let's take 2 4 1 3. So now those of you who are familiar with the permutation group S4 would already know what this element tells you. But to those who do not know, what it says is whatever object that you have at position number 2 will go to position number 4, and the object you have at position number 4 will go to position number 1, and your object at position number 1 will go to position number 3, and then the object at position number 3 goes to position number 2, and the object at position number 4 goes to position number 1, or the object at position number 1 goes to position number 3. Alright, so let's write down the representation of this element. So that representation can be written as representation of 2 4 1 3 is equal to a 4 cross 4 matrix, and that matrix will be written by using this property of this permutation group, that is, my object at position number 2 goes to position number 4, position number 4 goes to position number 1, and position number 1 goes to position number 3, and position number 3 then goes to position number 2. So my first column, I'll look at position number 1 goes to position number 3, so I'll have my non-zero entry at my third row in my first column. Now for second column, my object at position number 2 goes to position number 4, so I'll have my non-zero entry in my second column at my fourth row. So 0, 0, 0, and 1. Now for my object at position number 3 will go to position number 2, so I'll have my non-zero entry in my third column at second row, right? So 0, 1, 0, 0. Now for my last column, my object at position number 4 goes to position number 1, so I'll have my non-zero entry at first row in my fourth column, so 1, 0, 0, 0. And let's write this matrix a bit neatly. Alright, so this is how I wrote the representation of my element of an S4 group, namely the element 2, 4, 1, 3. Now let's say if you apply this matrix or operate with this matrix 2, 4, 1, 3 on your vector v2, for example, what should it do? What it should do is it should give you your vector v4. Now why is that? Because your permutation is taking you from position number 2 to position number 4, or the object at position number 2 is taken to position number 4. And likewise, for if you apply this to your vector v1, for example, it should give you your vector v3. And I would recommend you to do this as an exercise for yourself. Alright, so the action of the matrix D2413 on the 4 vectors basically mirrors precisely the action of the permutation 2413, that is this, the element 2413, on the 4 objects labeled as 1, 2, 3, 4, right? So now let's conclude this, and let me tell you or give you a way to think of the representation. So very roughly speaking, the representation of a group is something like a photograph of the group to the extent that it preserves the multiplicative structure of the group. So let's say that you go to a beach and you take a photograph of the beach, right? Now, the photograph of the beach represents the beach and is not the beach itself, right? So, in our case, the matrices represent the group, but is not the group itself. So I hope that this video gives you a very brief or an idea that what a representation of a group actually means. So that's it for this video.